Hello, good morning, dear students. In the last period, we have studied about the various types of catalysis. Today, we are going to understand the important features of this solid catalysis. So, we are going to study important features of solid catalysis. First feature that we can study here is activity of catalysis. So how we can make it active and how does it really work as an active catalyst? The activity of the catalyst depends upon the strength of chemisorption to a large extent. So mostly the activity depends upon chemisorption. Preferable conditions: the reactant must get adsorbed reasonably strongly on the surface of catalyst to become active. So it is necessary that the reactants are adsorbed in a great amount or in a enough amount on the surface of catalyst. However, the reactant must not get adsorbed strongly. The reactant must not get adsorbed so strongly that they become immobilized and other reactant get no space on the catalyst surface for adsorption. Here, this point says that the catalysis must be not so strong that the reactant molecules they do not removed, or they cannot be removed from the surface of the catalyst. So they should be adsorbed strong enough but not so strong that they cannot be removed. It has been found that for hydrogenation reaction, the catalytic activity increases from group number 5 to group number 11. So the metals belong to the D group. From group number 5 to group number 11 can be used into the reaction called hydrogenation. Hydrogenation means addition of hydrogen. There is one more specialty. Metals metals with maximum activity being shown by group 7 to 9 elements of the periodic table. So those elements which falls into the group number 7 to 9, they show special reactivity towards the reaction of hydrogenation that I have tried to explain here. That hydrogenation means addition of hydrogen. Now you can see here the group number I have written. The group number I have taken are 5, 6, 7, 8, 9, 10 and 11. I have shown you the various elements that are present in this group, and only this element 7, 8, 9, all these elements can be used as a catalyst into the hydrogenation reaction, but 7, 8, 9 group shows special characteristics, or you can say that I have written here maximum activity shown for the hydrogenation. We will see the example of hydrogenation of oxygen. H2 plus O2, it gives 2H2O, which is catalyzed by the platinum metal, which falls into the group number 10. Now we'll see about the selectivity. Selectivity of catalyst is ability to direct a reaction to yield a particular product. Now we'll try to understand what is this. A selectivity of catalyst is its ability to direct a reaction to yield a particular product. That means you can have various products when we use various catalyst. That is what we are going to see. For example, if we see starting with hydrogen and carbon monoxide and using different catalyst, we get different products. You can see here with the example you can understand that we will take carbon monoxide and 1 hydrogen, carbon monoxide and 2 hydrogen, carbon monoxide and 3 hydrogen, and we will use the various catalysts. For first reaction we will use copper, for second reaction we will use copper with zinc oxide and chromium oxide, and for the third reaction we will use nickel as a catalyst. You can easily see here that when we have the first reaction, the product is HCHO, which is methanol. In the second reaction we have the product CH3CHO, which is methanol, and in the third reaction we have methane and water as a products. So from the above reaction it can be inferred means it can be concluded that the action of catalyst is highly selective in nature. The action of catalyst is highly selective. That means a particular catalyst direct a reaction to a particular product. If we use various catalysts, we get various products. This is how we can understand. A given substance can act as a catalyst only in a particular reaction and not for all the reaction. This is what we need to understand, that a particular catalyst can catalyze the particular reaction. It cannot be used for all reaction as a catalyst. It means, what does it mean? It means substance which acts as a catalyst in one reaction may fail to catalyze the another reaction. Now we are going to understand one very important topic. This topic is asked in the exam very, like, quite a few times. So let us see this topic. This topic is named as a shape selective catalysis. Question: write a short note on shape selective catalyst, or write a short notes on zeolites. So these zeolites are also called the shape selective catalyst. Let us understand the definition of the shape selective catalyst. The the catalytic reaction depends upon the pore structure of the catalyst, and the size of the reactant and product molecule is called the shape selective catalysis. So this is how we can understand the definition. Now we'll understand the short notes points wise. Zeolites are shape selective catalysts. So zeolites are the examples of shape selective catalysis. They are aluminosilicates with three-dimensional network structure. The structure is available in three dimension, and they are aluminosilicates that we have studied into the 11th standard P block. The three-dimensional network solid, some silicon atoms are replaced by aluminum atoms, giving us aluminum oxygen silicon framework. So in zeolites, some silicon atoms are replaced by aluminum atoms, and we get aluminum oxygen silicon framework. Zeolites have pores on their surface, so they are called microporous. Zeolites are also called, or zeolites are considered as a microporous substances because they have pores on their surface, and they are available into the micro size, or they are available into the micron size. 1 micron is equal to 10 to the power minus 6 meter. Zeolites look like honeycomb. You might have seen a honeycomb which is having small pores, hexagonal pores on it. When we study these zeolites, they look like honeycomb with the help of microscope. So we can say that zeolites have honeycomb structures. Now, important point, the reaction taking place on the surface of zeolite depends upon, number one, the size and shape of the reactant and products molecules, and number two, the size of pores. Number two is the size of pores and cavity on the zeolites. So you can easily understand that the process, or the catalytic process, takes place on the zeolite depends upon the shape of the reactant and product molecules, and it is also depends upon the size of the pores or cavity on the zeolite surface. I hope, my dear students, you are enjoying. Happy learning.